Introduction to RFC 6234 and Sha-2. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics, focusing on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into RFC 6234, which defines the Sha-2 family of cryptographic hash functions. Sha-2 stands for Secure Hash Algorithm 2, and it's one of the most widely used hash functions in the world today. You'll find Sha-2 everywhere, from HTTPS connections to Bitcoin mining, from digital signatures to password storage systems. Understanding how Sha-2 works gives you insight into the cryptographic foundation of modern internet security. RFC 6234 is the authoritative document that precisely specifies how these algorithms work, replacing earlier RFCs and consolidating everything you need to know about Sha-224, Sha-256, Sha-384, Sha-512, Sha-512/224, and Sha-512/256. This presentation will break down complex mathematics and bit manipulations into understandable concepts. We will start with high-level concepts and progressively dive deeper into the implementation details. By the end, you will understand not just what Sha-2 does, but how and why it does it. Whether you're a developer implementing cryptographic systems, a security professional analyzing protocols, or just curious about the cryptography that protects your daily digital life, this comprehensive guide will give you the knowledge you need. We'll cover the mathematical foundations, the step-by-step algorithm, the different variants and when to use each one, security properties, real-world applications, and common pitfalls to avoid. What is a cryptographic hash function? Before we dive into Sha-2 specifically, let's establish what a cryptographic hash function is and why it matters. A hash function is a mathematical algorithm that takes an input of any size and produces a fixed size output called a hash or digest. Think of it like a fingerprint for data. Just as your fingerprint uniquely identifies you despite being much smaller than your entire body, a hash uniquely identifies data despite being much smaller than the original input. For a hash function to be cryptographic, meaning secure for use in security applications, it must satisfy several important properties. First is determinism. The same input must always produce the same output. If you hash the word hello today and tomorrow, you must get the same hash both times. The second property is the avalanche effect. Changing even a single bit in the input must completely change the output in unpredictable ways. For example, the hash of hello and the hash of hello must look completely different, even though only one letter changes. The third characteristic is one-way computation, or preimage resistance. It should be easy to compute the hash from the input, but it is virtually impossible to reverse the process and find an input that produces a specific hash. Fourth is collision resistance. It should be extremely difficult to find two different inputs that produce the same hash output. Fifth is second preimage resistance. Given one input and its hash, it should be hard to find a different input that produces that same hash. These properties make cryptographic hash functions incredibly useful for many security applications. They provide data integrity, allowing you to verify that data has not been tampered with. They enable digital signatures by providing a fixed-size representation of any message. They support password storage by providing one-way hashing. They enable proof-of-work systems like Bitcoin mining. Sha-2 provides all these properties with strong security guarantees that have withstood decades of cryptanalytic scrutiny. Sha-2 Family Overview. The Sha-2 family consists of 6 hash function variants, and understanding the differences between them helps you choose the right one for your needs. Sha-256 produces a 256-bit or 32-byte hash output. It processes messages in 512-bit blocks and is the most commonly used variant. When people say Sha-2 without specifying a variant, They usually mean SHA-256. SHA-224 is essentially SHA-256 with the output truncated to 224 bits. It uses the same algorithm, but with different initial values. SHA-512 produces 5 12-bit output and processes messages in 10 24-bit blocks. It uses 64-bit arithmetic internally compared to SHA-256's 32-bit arithmetic, making it faster on 64-bit processors. SHA-384 is SHA-512 truncated to 384 bits, using different initial values but otherwise identical to SHA-512. The newer SHA-512/256 variant runs the full SHA-512 algorithm, but outputs only 256 bits. Why would you use this instead of SHA-256? Because on 64-bit systems, SHA-512/256 can be significantly faster than SHA-256 while providing the same output size. Similarly, SHA-512/224 provides 224-bit output using the SHA-512 algorithm. All these variants share the same fundamental structure called the Merkle-Damgard construction. They differ in their word size, 32-bit versus 64-bit, the number of rounds they perform, the size of message blocks they process, and their initial hash values. The choice between variants depends on your security requirements, performance needs, and system architecture. The beauty of having these variants is that they provide flexibility without requiring you to learn completely different algorithms. Once you understand SHA-256, you understand the core concepts behind all SHA-2 variants. High-level algorithm structure. Now let's look at the high-level structure of how SHA-256 works, which will give us a roadmap for the detailed sections to come. The algorithm consists of 5 main phases. Phase 1 is preprocessing and padding. SHA-256 requires that the input message be a multiple of 512 bits. If your message is not already a multiple of 512 bits, which it almost never is, we pad it according to a specific scheme. We append a single 1-bit, then add 0 or more 0 bits, and finally append a 64-bit representation of the original message length. This ensures that messages of different lengths, even those differing by 1 bit, get padded differently. Phase 2 is parsing the message into blocks. After padding, we divide the message into 512-bit blocks. Each block will be processed sequentially. Phase 3 involves setting initial hash values. We initialize 8 32-bit variables, H0 through H7, with specific constant values. These initial values are carefully chosen to have no hidden weaknesses. Phase 4 is the main processing loop. For each 512-bit message block, we run a compression function that thoroughly mixes the block with the current hash value. This compression function is where most of the algorithmic complexity resides, involving 64 rounds of bit manipulation operations. After processing a block, its output becomes the starting hash value for the next block. This chaining ensures the final hash depends on every part of the input message. Phase 5 is producing the final hash. After all message blocks have been processed, we concatenate the 8 hash variables H0 through H7 to produce the final 256-bit output. This high-level structure, called the Merkle-Damgard construction, is proven to have strong security properties. If the compression function is secure against collisions, then the entire hash function is secure against collisions, even when processing arbitrarily long messages. Message padding and parsing. Let's dive into the first concrete steps of SHA-256, the message padding and parsing. This might seem like a boring administrative detail, but the padding scheme is crucial for security. Here is exactly how padding works. Suppose your message, M, has a length of L bits. First, append a single 1 bit to the end of your message. Your message is now L plus 1 bits long. Next, append K0 bits where K is the smallest non-negative integer such that L plus 1, plus K, plus 64 is a multiple of 512. In other words, we are adding enough zeros so that when we later add 64 more bits, we will have complete 512-bit blocks. Finally, append L as a 64-bit big Indian integer. This tells the algorithm what the original message length was, before padding. Let's walk through an example. Suppose we want to hash the 24-bit message, which is the ASCII encoding of ABC after appending the 1 bit. We have 25 bits. We need to add k zeros where 25 plus k plus 64 equals a multiple of 512. That gives us k equals 423. So we append 1 bit, then 423 0 bits, then the 64-bit value 24 in binary. The result is exactly 512 bits, one complete message block. Why is this padding scheme important? The 1 bit ensures that even empty messages get padded differently from messages that end in zeros. The length field at the end prevents length extension attacks where an attacker appends data to a message and computes a valid hash. The padding makes it impossible for two different messages to pad to the same value. Once the message is padded, we parse it into n 512-bit blocks M1 through Mn. Each block is then further divided into 16 32-bit words M0 through M15 for processing. The parsing is straightforward, just splitting the bits, but the padding is where the clever design ensures security. Message schedule and word expansion. Each 512-bit message block is expanded into a message schedule of 64 32-bit words. This expansion is a key part of the mixing and diffusion properties of Sha-256. Here's how it works. We start with the 16 32-bit words that came directly from parsing the message block, words W0 through W15. Then we generate words W16 through W63 using a specific formula. For each word WT, where T goes from 16 to 63, we compute WT equals sigma 1 of W at position T-2, plus W at position T-7, plus sigma 0 of W at position T-15, plus W at position T-16. All arithmetic is performed modulo 2 to the 32, meaning we work with 32-bit unsigned integers and any overflow wraps around. Now what are these sigma functions? They are mixing functions designed to create complex relationships between bits. Sigma 0 of x equals ROTR 7 of x XOR ROTR 18 of x XOR SHR 3 of x. ROTR stands for rotate right, which shifts bits right with wraparound. SHR is shift right, which shifts bits right with zeros filling in from the left. XOR is exclusive or a bitwise operation. Sigma 1 of x equals ROTR 17 of x XOR ROTR 19 of x XOR SHR 10 of x. The different rotation amounts, 7 versus 18, 17 versus 19, and the XOR operations create thorough bit mixing. Why expand 16 words into 64? This expansion ensures that changing any single bit in the input affects many words in the schedule, which then affects many rounds of the compression function. It is a crucial part of achieving the avalanche effect. The specific rotation amounts were carefully chosen through cryptanalytic study to maximize diffusion while keeping the computation efficient. Each generated word WT depends on words from 4 different earlier positions in the schedule. This creates a complex web of dependencies that makes it extremely difficult for an attacker to craft inputs with specific properties. The compression function. The compression function is where the real magic happens in Sha-256. This is the core mixing operation that processes each message block and produces the hash. The function maintains 8 32-bit working variables A, B, C, D, E, F, G, and H at the start of processing each message block. These variables are initialized to the current hash value, either the initial constants for the first block, or the intermediate hash from the previous block. Then we run 64 rounds of processing, one for each word in the message schedule. Each round performs the following operations. First, we compute two temporary values. T1 equals h plus the sigma 1 function of e, plus the ch function of e, f, and g, plus the round constant kt, plus the message schedule word wtt2 equals the sigma 0 function of a, plus the maj function of a, b, and c. The sigma functions are different from the sigma functions we used in the message schedule. These operate on the working variables using different rotation amounts. Sigma 1 of x uses rotations of 6, 11, and 25 bits. Sigma 0 of x uses rotations of 2, 13, and 22 bits. The ch function stands for choose. It outputs f if e equals 1, or g if e equals 0, for each bit position. Mathematically, ch of e, f, g equals e and f XOR not e and g. The maj function stands for majority. It outputs the majority bit among a, b, and c at each position. Mathematically, maj of a, b, c equals a and b XOR a and c XOR b and c. After computing T1 and T2, we update the working variables. H gets the value of g, g gets f, f gets e, e gets d plus T1, d gets c, c gets b, b gets a, and a gets T1 plus T2. This creates a pipeline where values flow through the variables, being mixed and modified at each step. After all 64 rounds, we add the original starting values back to a through h to produce the intermediate hash value for this block. Bitwise operations explained. SHA-256 relies heavily on bitwise operations, so let's make sure we understand what these are and why they are used. A bitwise operation works on individual bits in binary numbers. The most common ones in SHA-256 are AND, OR, XOR, NOT, rotate, and shift. And takes 2 bits and outputs 1 only if both inputs are 1. For example, 1010 and 1100 equals 1000. Or outputs 1 if either input is 1, so 1010 or 1100 equals 1110. XOR, or exclusive OR, outputs 1 if the inputs are different, so 1010 XOR 1100 equals 0110. NOT flips all bits, so not 1010 equals 0101. Rotate right by end positions takes bits and shifts them right, with bits that fall off the right end wrapping around to the left. For example, rotating 10110011 right by 3 positions gives 01110110. Shift right is similar but does not wrap. The bits that fall off disappear and zeros come in from the left. Why use these operations? First, they are extremely fast on computer hardware. Modern CPUs can perform billions of these operations per second. Second, they create nonlinearity in the algorithm. Simple operations like addition are linear and potentially vulnerable to mathematical attacks. XOR and the other bitwise operations create complex relationships between input and output that resist analysis. Third, they provide diffusion. Changing one input bit affects many output bits in unpredictable ways. The specific combination of rotations, shifts, and XORs in SHA-256 was carefully chosen to maximize diffusion while remaining efficient to compute. The rotation amounts in sigma 0, sigma 1, sigma 0, and sigma 1 are different by design. This ensures that each function contributes unique mixing to the overall algorithm. The choice of these operations is backed by decades of cryptanalytic research, showing that this combination provides strong security against known attacks. Initial hash values and constants. SHA-256 uses carefully chosen initial values and constants that might seem arbitrary but are actually mathematically significant. Let's understand where these numbers come from and why they matter. The 8 initial hash values, H0 through H7, are set at the very beginning, before processing any message blocks. These are 32-bit numbers that look random, but they are actually the first 32 bits of the fractional parts of the square roots of the first 8 prime numbers: 2, 3, 5, 7, 11, 13, 17, and 19. For example, the square root of 2 is approximately 1.41, ending with 6,2, and the fractional part is 0.41, ending with 6,2. Converting this to binary and taking the first 32 bits gives the hexadecimal value 0x6a, ending with 67, which is H0. Why use these specific numbers? They are nothing up my sleeve numbers, meaning they are derived from a simple mathematical formula that anyone can verify, proving the designers did not choose values with hidden weaknesses. The 64 round constants, K0 through K63, follow a similar pattern. They are the first 32 bits of the fractional parts of the cube roots of the first 64 prime numbers. The cube root of 2 is approximately 1.259921, with a fractional part of 0.259921, giving K0 equals beginning with 0x42 ending with 98. These constants inject randomness into each round, ensuring that each of the 64 rounds is slightly different. Without these constants, identical message words in different rounds would produce identical transformations, which could create patterns an attacker might exploit. These constants are mathematically derived from prime numbers, ensuring they have good statistical properties. They appear random, have no obvious patterns, and distribute evenly across the possible values. This is important because any pattern in the constants could translate to a weakness in the hash function. Step-by-step SHA-256 computation. Let's walk through a complete SHA-256 computation step by step so you can see how all the pieces fit together. Imagine we want to hash the message ABC. The first step is preprocessing and padding. The ASCII values of A, B, and C are 97, 98, and 99 in decimal. Or, in binary, beginning with 01, ending with 01, for the first value, beginning with 01, ending with 10, for the second value, and beginning with 01, ending with 11, for the third value. This gives us 24 bits. We then append a 1 bit, followed by 423 0 bits, to reach 448 bits. Next, we append 64 bits, representing the length 24, creating one complete 512-bit block. Step 2 is to parse words. We split the 512-bit block into 16 32-bit words W0 through W15. The first 3 words contain our message. The rest are mostly zeros, except for W15, which contains the length. Step 3 is expand the message schedule. We compute words W16 through W63 using the sigma functions and previous words, creating 64 total words. Step 4 is to initialize the working variables. We set A through H to the initial hash values, which are constants derived from the square roots of primes. Step 5 is run 64 rounds. In round 0, we take W0 and K0, compute T1 and T2 using our CH, Maj, sigma functions, and update all 8 working variables. In round 1, we use W1 and K1 and repeat the process. This continues through round 63. Each round thoroughly mixes the current state with a message word and round constant. Step 6 is to compute the intermediate hash. After all 64 rounds, we add the original initial values to the final A through H values. For ABC, since we only have one block, this intermediate hash is also our final hash. Step 7 is format the output. We concatenate H0 through H7 to form the 256-bit output, typically displayed as 64 hexadecimal characters. For ABC, the SHA-256 hash is beginning with BA ending with 5AD. This entire process is deterministic and will always produce the same output for the same input. Processing large files blockchaining detail. Now that we understand how SHA-256 processes a small message like ABC, let's examine what happens when we hash a large file, say a 1 megabyte file. This is where the iterative block-by-block nature of SHA-256 really shows its elegance and efficiency. First, let us understand the scale. 1 megabyte equals 1,048,576 bytes, which is 8,388,608 bits. Since SHA-256 processes data in 512-bit blocks, with each block equaling 64 bytes, we need to divide our file into blocks. The calculation involves dividing 1,048,576 bytes by 64 bytes per block, resulting in 16,384 blocks. Therefore, our 1 MB file will be processed as 16,384 separate 512-bit blocks. Step 1 is initialization. We start by setting our 8 hash variables to the initial constants. Remember from slide 9, these are the nothing up my sleeve numbers derived from the square roots of the first 8 prime numbers. H0 equals beginning with 0x6 ending with 67, which comes from the square root of 2. H1 equals beginning with 0xbb ending with 85, from the square root of 3. H2 equals beginning with 0x3c ending with 72, from the square root of 5. H3 equals beginning with 0xa5 ending with 3a, from the square root of 7. H4 equals beginning with 0x51 ending with 7f, from the square root of 11. H5 equals beginning with 0x9b ending with 8c, from the square root of 13. H6 equals beginning with 0x1f ending with 9b, from the square root of 17. And H7 equals beginning with 0x5b ending with 19, from the square root of 19. These 8 32-bit values are our starting hash state before processing any blocks. They are the same fixed constants used every time anyone computes SHA-256 for any message. Step 2 is processing block 1. We read the first 64 bytes from the file, bytes 0 through 63. Let's say these bytes contain some actual file data, maybe the beginning of a JPEG image or a text document. These 512 bits become our first message block. We parse these 512 bits into 16 32-bit words W0 through W15. Then we expand these 16 words into 64 words using the message schedule formulas with sigma 0 and sigma 1. Now we initialize our working variables a, b, c, d, e, f, g, h to our current hash state, which for block 1 is still the initial constants. So, a equals beginning with 0x6a and ending with 67, b equals beginning with 0xbb and ending with 85, and so on. We run 64 rounds of the compression function. In round 0, we compute T1 equals H plus sigma 1 of E plus CH of E, F, G plus K0 plus W0. We compute T2 equals sigma 0 of A plus Maj of A, B, C. Then we shift all the variables. After round 0, A gets a new value of T1 plus T2. Let's say it becomes beginning with 0x8f and ending with 2ab gets the old A value of beginning with 0x6a and ending with 67. E gets D plus T1, maybe beginning with 0xc7 and ending with B4. And so on. We continue through all 64 rounds, with each round further mixing the values. After round 63, we have final working variable values. Let's say A is now beginning with 1 2, ending with CD. B is beginning with 5 6, ending with 9 0, and so on through H. Now comes the crucial step that many people miss. We don't just use these final working values as our output. Instead, we add these final working values back to the values we started with for this block. Remember, we started block 1 with the initial constants. So, the new H0 equals the initial H0 value, beginning with 6 ending with 6 7, plus the final A value, beginning with 12 ending with CD, which equals beginning with 7C ending with 34. The new H1 equals the initial H1, beginning with BB ending with 85, plus the final B value, beginning with 56 ending with 90, which equals, let's say, beginning with 12 ending with 15. We do this addition for all 8 values. These 8 new values, H0 through H7, after the addition, are our hash state after block 1. Let's call them H0_1 equals beginning with 7C and ending with 34. H1_1 equals beginning with 12 and ending with 15, and so on through H7_1. These values represent the cumulative effect of processing the first 64 bytes of our file, mixed with the initial constants. Step 3 is processing block 2, and this is where the chaining becomes clear. Now we read bytes 64 through 127 from the file, the next 64 bytes. This becomes block 2. We parse these into 16 32-bit words, expand to 64 words using the message schedule. Here is the key difference. When we initialize our working variables A through H for processing block 2, we do not use the original initial constants anymore. Instead, we use the hash state that came out of block 1. So A equals H01, which is beginning with 7C ending with 34. B equals H11, which is beginning with 12 ending with 15. C equals H21, and so on through H equals H71. We are starting block 2 with the output from block 1. Now, we run 64 rounds again, using block 2's message schedule words W0 through W63, and the same round constants K0 through K63. Each round mixes block 2's data with the hash state from block 1. After 64 rounds, we have new working variable values. Let's say A is now 0x, beginning with 9f, ending with 6c, and B is 0x, beginning with 3c, ending with 9e. We add these to our starting values for block 2, which, as you recall, were the outputs from block 1. The new H0 equals H01, which was hexadecimal beginning with 7c and ending with 34, plus the final A, hexadecimal beginning with 9f and ending with 6c. This result is hexadecimal beginning with 1c and ending with a 0. This becomes H02. The new H1 equals H11 plus final B, giving us H12. This gives us H02 through H72, the hash state after block 2. We have now incorporated the first 128 bytes of the file into our evolving hash state. Step 4 is processing block 3. We read bytes 128 through 191. Parse and expand. Initialize working variables A through H to H02 through H72, the output from block 2. Run 64 rounds with block 3's data. Add the final working values back to H02 through H72 that we started with. Get H03 through H73. This pattern continues. Block 4 starts with the output from block 3. Block 5 starts with the output from block 4. Each block's processing depends on all previous blocks through this chaining mechanism. If you change even one bit in block 1, it affects the output hash state from block 1. This, in turn, affects how block 2 is processed, which then affects block 3, and so on, all the way to the end. This is how SHA-256 achieves its avalanche property across large files. The hash state acts as a running summary of everything seen so far. After processing all 16,384 data blocks, we have hash state H0 16,384 through H7 16,384. Step 5 is the final padding block. We create block 16,385 containing just padding, a 1-bit, zeros, and the length. We process this one more time using H0 16,384 through H7 16,384 as our starting values. The output from this final padding block H0 16385 through H7 16385 is our final hash. We concatenate these 8 32-bit values to get our 256-bit output. The beauty is that at no point did we need more than about 384 bytes of memory, consisting of the current block, hash state, and working variables, even though we processed over 1 million bytes of data. Each block is processed and then discarded because its effect is captured in the updated hash state that flows to the next block. SHA 512 and 64-bit variants. SHA 512 is the 64-bit cousin of SHA 256, and understanding their differences helps illuminate why we have multiple variants. SHA 512 uses fundamentally the same algorithm structure as SHA 256 but scales everything up. Instead of processing 5 12-bit message blocks, SHA 512 processes 10 24-bit blocks. Instead of maintaining 8 32-bit working variables, it uses 8 64-bit working variables. Instead of 64 rounds, it runs 80 rounds. The message schedule expands each 10 24-bit block into 80 64-bit words instead of 64 32-bit words. The rotation and shift amounts in the sigma and sigma functions are different, chosen to work well with 64-bit words. For example, sigma 0 uses rotations of 28, 34, and 39 bits instead of 2, 13, and 22. The round constants are still derived from cube roots of primes, but now we take the first 64 bits of the fractional parts of the first 80 primes. The initial hash values come from the first 64 bits of the fractional parts of square roots of the first 8 primes. Why create this 64-bit variant? Modern processors with 64-bit architectures can process 64-bit operations just as efficiently as 32-bit ones, making SHA 512 actually faster than SHA 256 on these systems despite producing twice the output. SHA 512 also provides a larger security margin. With 512 bits of output, the birthday attack bound is at 2 to the 256 operations instead of 2 to the 128 for SHA 256. SHA 384 is simply SHA 512 with different initial values and the output truncated to 384 bits. The newer SHA 512/256 variant runs the full SHA 512 algorithm but uses different initial values and truncates to 256 bits. Why would you use SHA 512/256 instead of SHA 256? Because on 64-bit systems, SHA 512/256 can actually be faster while providing the same output size. Security Properties Deep Dive. Let us examine the security properties that make SHA-2 suitable for cryptographic applications. Property 1 is preimage resistance, also called the one-way property. Given a hash output H, it should be computationally infeasible to find any message M such that hash of M equals H for SHA-256. This means an attacker would need to try approximately 2 to the 256 different inputs before expecting to find one that hashes to a target value. That is more atoms than exist in the observable universe. Property 2 is second preimage resistance. Given a message M1, it should be hard to find a different message M2 such that hash of M1 equals hash of M2. This is crucial for digital signatures. An attacker with a signed document should not be able to find a different document with the same hash, and therefore, the same signature. Property 3 is collision resistance. It should be hard to find any two different messages that hash to the same value. Due to the birthday paradox, the expected work to find a collision is about 2 to the 128 operations for SHA-256, which is still astronomically large. Property 4 is avalanche effect. Changing even one bit in the input should change approximately half the bits in the output, and the changes should appear random. SHA-256 achieves excellent avalanche effect through its multiple rounds of mixing. Property 5 is near uniform distribution. Hash outputs should be evenly distributed across the entire output space with no obvious patterns. SHA-2 achieves this through the carefully designed mixing functions and route constants. As of 2025, no practical attacks against SHA-2 have been found. The best theoretical attacks on reduced round versions still require more computation than is feasible. This strong security record, combined with rigorous analysis by cryptographers worldwide, gives us confidence that SHA-2 is secure for current applications. Real-world applications. SHA-2 is everywhere in modern computing. Let's explore some real-world applications to understand why this algorithm matters so much. Application 1 is TLS and HTTPS. When you visit a secure website, your browser uses SHA-256 or SHA-384 to verify digital signatures on certificates and to derive encryption keys through protocols like HKDF. Every time you see that padlock icon, SHA-2 is working behind the scenes. Application 2 is Bitcoin and blockchain. Bitcoin uses SHA-256 twice for its proof-of-work mining algorithm. Miners repeatedly hash block headers searching for a hash below a target threshold. Bitcoin's security fundamentally relies on SHA-256, a collision resistance and one-way property. Application 3 is digital signatures. Algorithms like RSA, ECDSA, and EDDSA hash the message before signing, typically using SHA-256 or SHA-512. The hash ensures you are signing a fixed size value regardless of message length and provides collision resistance. Application 4 is password hashing, though SHA-2 alone is not recommended for this. Systems typically use SHA-256 or SHA-512 as part of password-based key derivation functions like PBKDF2 or as the underlying hash in bcrypt and Argon2. Application 5 is file integrity and checksums. Software distributions often provide SHA-256 hashes so you can verify your download was not corrupted or tampered with. Git uses SHA-1 currently but is migrating to SHA-256. Application 6 is HMAC message authentication. When you need to authenticate messages with a shared secret, HMAC SHA-256 is a popular choice, providing both integrity and authenticity. Application 7 is random number generation. Many cryptographically secure random number generators use SHA-2 as their mixing function. Application 8 involves certificate transparency logs that use SHA-256 to create Merkle trees of certificates. These diverse applications demonstrate SHA-2's versatility and trustworthiness. Choosing between Sha-2 variants. With 6 different SHA-2 variants available, how do you choose which one to use? Let's break down the decision factors. For most general-purpose applications, SHA-256 is the recommended choice. It provides 128-bit collision resistance and 256-bit preimage resistance, which is more than sufficient for any foreseeable threat. It is widely supported in libraries and hardware, well-studied, and efficient on both 32-bit and 64-bit systems. Use SHA-256 for digital signatures, TLS, general data integrity, password-based key derivation, and when you need broad compatibility. Choose SHA-512 when you are working primarily on 64-bit systems and want maximum performance for large data volumes. On modern 64-bit processors, SHA-512 can actually be faster than SHA-256 per byte processed, even though it produces twice the output. SHA-512 also provides a larger security margin with 256-bit collision resistance, which might be desirable for extremely long-term security requirements or high-value applications. Use SHA-384 when you need the security properties of SHA-512 but want a shorter output, perhaps for bandwidth or storage efficiency. It is common in high-security government and financial applications. SHA-512/256 is interesting because it gives you SHA-256-sized output with the performance characteristics of SHA-512 on 64-bit systems. It is useful when you are constrained to 256-bit outputs but want optimal performance. SHA-224 and SHA-512/224 are less common but useful when you have strict output size requirements, perhaps for legacy protocol compatibility, or when you need to fit hashes into fixed database fields. Performance considerations matter. Measure on your target hardware. Security considerations matter too. Ensure your chosen variant provides adequate collision and preimage resistance for your threat model. Compatibility matters. Ensure your platforms and protocols support your choice. When in doubt, SHA-256 is a safe default that is universally supported and well understood. Implementation best practices. When implementing or using Sha-2 in your applications, following best practices ensures security and correctness. Practice 1 is to use established libraries. Do not implement Sha-2 yourself unless you are a cryptography expert. Use well-tested libraries like OpenSSL, libsodium, cryptography for Python, the Java cryptography architecture, or crypto in Node.js. These implementations have been audited and optimized. Practice 2 is to verify with test vectors. RFC 6234 and NIST provide official test vectors. When integrating a Sha-2 implementation, run these tests to ensure correctness. One incorrect bit in your implementation could undermine all security. Practice 3 is to use constant time implementations when hashing secrets. While Sha-2 itself does not require constant time execution for most applications, if you are using it in a context where timing information could leak secrets, for example, in certain HMAC applications, use implementations designed to resist timing attacks. Practice 4 is, do not truncate outputs yourself. If you need a shorter hash, use the official truncated variants, like SHA-224, rather than just taking the first n bits of SHA-256. The truncated variants use different initial values specifically designed for security. Practice 5 is to understand your threat model. Sha-2 is collision-resistant but not collision-proof. For digital signatures and certificates, collision resistance matters a lot. For file integrity checking with no adversarial tampering, even a weaker hash might suffice. Practice 6 is to combine with other security measures. Sha-2 is a tool, not a complete solution. For password storage, use it inside a proper password hashing function. For message authentication, use it with HMAC. For encryption, use authenticated encryption, not hash then encrypt. Practice 7 is to plan for hash agility. Design systems that can switch hash algorithms if needed. While Sha-2 is secure now, cryptography evolves, and you may need to migrate to Sha-3 or future algorithms. Practice 8 is to be aware of performance characteristics. Hashing large files can be CPU intensive. Consider streaming implementations for large data and hardware acceleration when available. Test vectors and validation. RFC 6234 provides comprehensive test vectors for all SHA-2 variants, and these are crucial for validating implementations. Let's look at some key test cases. For SHA-256, the simplest test is the empty string. Hashing 0 bytes should produce beginning with E3B0 ending with B855. This might seem trivial, but it tests that your padding implementation correctly handles the edge case of no message data. The single block test uses a BC as input, producing the hash beginning with BA78 ending with 15AD. This is the most famous SHA-256 test vector and tests basic single block processing. The two-block test uses beginning with a BCD-BC ending with NOPQ as input, which is carefully chosen to be 448 bits long before padding, creating exactly 2 message blocks after padding. This tests the chaining mechanism between blocks. There is also a million-character test where you hash the letter O repeatedly, testing the implementation's ability to handle large inputs. For SHA-512, similar test vectors exist but with different output lengths. Each test vector is precisely specified with the input message in hexadecimal or ASCII, and the expected output hash in hexadecimal. When implementing SHA-2, you should run all these test vectors and verify your outputs match exactly, byte for byte. Any discrepancy, even a single bit flip, indicates a bug in your implementation. Many cryptographic libraries include these test vectors in their unit test suites. If you are auditing or reviewing SHA-2 code, checking that it passes all RFC test vectors is a fundamental verification step. NIST also provides additional test vectors for various message lengths and patterns, including test vectors specifically designed to exercise edge cases and potential implementation pitfalls. SHA-2 versus SHA-1 versus SHA-3. Understanding how SHA-2 compares to its predecessor SHA-1 and its successor SHA-3 provides important context. SHA-1, published in 1995, produces 160-bit hashes and was widely used for many years. However, theoretical attacks were published in 2005, and in 2017, researchers demonstrated a practical collision attack, finding two different PDF files with the same SHA-1 hash. This collision attack does not mean SHA-1 is completely broken, but it is no longer suitable for security-critical applications like digital signatures and certificates. Major web browsers stopped accepting SHA-1 certificates, and Git is migrating away from it. SHA-1's weakness motivated the development and adoption of SHA-2. SHA-2 was actually published in 2001, before SHA-1's vulnerabilities were demonstrated, but it was not widely adopted until SHA-1's problems became apparent. SHA-2 uses a fundamentally similar design to SHA-1 but with larger state variables, more rounds, and careful improvements to resist known attack techniques. As of 2025, SHA-2 remains secure with no practical attacks. SHA-3, published in 2015, uses a completely different internal structure based on the Keccak sponge construction. It was developed through a public competition run by NIST, similar to how AES was selected. SHA-3 is not meant to replace SHA-2 because SHA-2 is not broken. Instead, SHA-3 provides diversity. If a fundamental flaw were discovered in SHA-2's design, SHA-3's different construction would likely not share the same vulnerability. SHA-3 is gradually being adopted, but SHA-2 remains the dominant choice for most applications. SHA-3 offers some interesting properties like variable length output and built-in support for authenticated encryption modes, but it is typically slower than SHA-2 on general-purpose CPUs. For new projects today, SHA-2, specifically SHA-256 or SHA-512, is the recommended choice. Use SHA-3 when you specifically need its unique properties or want defense in depth through algorithm diversity. Hardware acceleration and performance. SHA-2's widespread use has driven the development of hardware acceleration, making it incredibly fast on modern systems. Let's explore the performance landscape. Intel and AMD processors since 2013 include SHA extensions, special CPU instructions specifically designed for SHA-256 and SHA-512 computation. These instructions, like SHA-256 RNDS2 and SHA-256 MSG1, can compute multiple SHA-256 rounds in a single instruction, providing massive speedups. With these extensions, a modern CPU can hash over 2 GB per second using SHA-256. ARM processors also include cryptographic extensions with instructions for SHA-1 and SHA-2. Apple's M-series chips excel at cryptographic operations including SHA-256. Even without hardware extensions, SHA-2 benefits from general CPU optimizations. The algorithm uses only simple operations like addition, bitwise logic, and rotations that map efficiently to CPU instructions. SIMD instructions like AVX2 can process multiple hash operations in parallel. For systems processing large volumes of data, hardware offload is available. Network interface cards can perform SHA-2 hashing in hardware, useful for applications like IPsec VPNs. Some SSDs include hardware SHA engines for data verification. GPS can compute SHA-2 hashes massively in parallel, which is why cryptocurrency mining uses GPU farms. ASICs, application-specific integrated circuits, designed specifically for SHA-256 mining can compute trillions of hashes per second, though they are only economical for Bitcoin mining. In terms of software performance, SHA-256 typically runs at 100 to 400 megabytes per second on a single CPU core without hardware acceleration, and over 2 gigabytes per second with SHA extensions. SHA-512 is faster on 64-bit systems, reaching similar or higher throughput. For embedded systems with limited processing power, SHA-256 remains practical. Even a low-power ARM Cortex-M processor can hash several megabytes per second. The lesson is that SHA-2 performance is excellent on essentially all modern hardware, which contributes to its universal adoption. Common pitfalls and mistakes. Even though SHA-2 is well defined, there are common mistakes developers make when using it. Let's review these so you can avoid them. Mistake 1 is using SHA-2 directly for password storage. SHA-2 is too fast for passwords. An attacker can compute billions of hashes per second trying to crack passwords. Always use a proper password hashing function like bcrypt, argon2, or pbkdf2 with SHA-2 as the underlying primitive. Mistake 2 is comparing hashes using string comparison functions. When verifying hashes in security contexts, use constant time comparison to prevent timing attacks. Standard string comparison might return early when it finds a difference, potentially leaking information about the hash. Mistake 3 is truncating outputs incorrectly. Don't just take the first n bits of SHA-256 if you need a shorter hash. Use SHA-224 or SHA-512/256, which are designed for truncation. Mistake 4 is not handling the empty string case. Make sure your implementation correctly hashes empty inputs. This is a common source of bugs. Mistake 5 is using SHA-2 where authentication is needed. SHA-2 provides integrity, but not authenticity. An attacker can modify data and compute a new hash. For authentication, use HMAC-SHA-2 or authenticated encryption. Mistake 6 is implementing SHA-2 yourself. Unless you're a cryptography expert, use established libraries. Subtle implementation bugs can completely break security. Mistake 7 is not validating inputs. While SHA-2 handles any input, your application might have constraints. Validate input lengths and formats before hashing. Mistake 8 is assuming collision resistance equals unforgeability. For digital signatures, collision resistance is necessary but not sufficient. The signature algorithm itself must be secure. Mistake 9 is using the same hash for different purposes without domain separation. If you're hashing different types of data, prefix them with different identifiers to prevent cross-protocol attacks. Mistake 10 is ignoring performance at scale. Hashing terabytes of data takes time even with fast algorithms. Plan accordingly and consider streaming implementations. Future of SHA-2 in conclusion. As we wrap up this comprehensive guide to SHA-2, let's look at the future outlook and key takeaways. SHA-2 has proven to be remarkably resilient. Published in 2001, it has withstood over 2 decades of intense cryptanalytic scrutiny without any practical attacks being discovered. The algorithm's design, with its multiple rounds of complex mixing operations, carefully chosen constants, and strong mathematical foundation, has stood the test of time. Looking forward, SHA-2 will continue to be the dominant hash function for many years to come. It's deeply embedded in countless protocols, standards, and systems worldwide. The investment in hardware acceleration, including dedicated CPU instructions and specialized mining ASICs, ensures that SHA-2 will remain performant and economical. What about quantum computers? While quantum computers could theoretically reduce the effective security strength of hash functions using Grover's algorithm, the reduction is less severe than for asymmetric cryptography. SHA-256's security would be reduced from 256 bits to 128 bits in a quantum world, which is still considered secure. SHA-512 would retain 256-bit security. So even in a post-quantum world, SHA-2 remains viable. SHA-3 provides important diversity. If a breakthrough attack against the Merkle-Damgard construction were discovered, SHA-3's different sponge construction would likely remain secure. For high-security applications, using both SHA-2 and SHA-3 provides defense in depth. The key takeaways are these. SHA-2, particularly SHA-256 and SHA-512, represents a masterpiece of cryptographic engineering. It provides strong security guarantees backed by extensive analysis. It offers excellent performance on all modern platforms. It's universally supported across languages and systems. Understanding how SHA-2 works, from the high-level Merkle-Damgard structure down to the bitwise operations in each round, gives you deep insight into practical cryptography. Whether you're building secure systems, analyzing protocols, or just satisfying your curiosity, this knowledge of SHA-2 is foundational to modern computer security. Thank you for your attendance. Please consider subscribing to the channel.